Hello everyone. In our last classes we have discussed the basics for symmetry. Also we have started with the rotational axis of symmetry. We have taken some examples how to show the operation which is being carried out in different molecules. We have taken some simplest of the molecules, for example water, H2O, ammonia, NS3, and also we have taken a little bit typical molecules such as allene. In this class, let us see about the plane of symmetry, which also is a very important symmetry element, and how to show the planes in the various given molecules. Whenever a molecule is given, how to immediately identify whether it is a vertical plane, horizontal plane or dihedral plane. At the end of the session, I will also give you some logics to get these planes. So let us begin with plane of symmetry. Plane of symmetry indicated by sigma. We also call it as a sigma symmetry or reflection symmetry. Plane is the element, whereas reflection is the operation. Just as we have seen in the case of axis, when we say axis of symmetry, it is axis is an element, and we also say rotational axis of symmetry where the rotation forms the operation. Both are intricately related, symmetry element as well as symmetry operation, both are intricately related, so we don't differentiate them. We simply call it as rotational axis of symmetry where axis form the element whereas rotation form the operation. Just in a similar way, plane forms the element whereas reflection is the operation, but we simply give the name as plane of symmetry or reflection symmetry. So what exactly is this reflection symmetry? We will first try to understand, and then we will take up some examples. We will try to show what kind of planes that are present in the given example. When it comes to the plane, in the beginning classes we have taken three different planes: sigma xy, sigma xz and sigma yz. I will be just drawing those planes with reference to the convention of these three Cartesian coordinates. Well, the convention is x facing towards you, y towards your right and left, and z above and below, or towards your top and bottom. So with respect to that, when I say sigma xy is this plane. Since it is a two-dimensional board, x might be looking down, but sigma xy means this plane. So if at all I show my hand in this way, you have to imagine that this is a xy plane. Then this forms xz plane. So however I may show, this is a xz, or even if I show it this way, this is also, this is an xz. Let me show it with my right hand. This is xz, yz and xy plane. So suppose if I show my hand this way, it is xy. Even if I show this way, this is also xy. You need not get confused. So let me show this way or this way. You have to imagine this as xy. Let me show this way, it is xz, or I may show this way, this is also xz. And finally this is yz, or I may show it this way, yz. So you have to remember all these planes. With respect to this, I am drawing them. To represent xy plane, I may draw a full plane, or only half a plane can be represented. So even if I draw it this way, you have to imagine that it is a xy plane. Coming to the xz, this is a xz plane. So again we can represent with a half plane. This is xz. For our easy representations, every time you need not draw a full plane, we can just go by half a plane. In a similar way for xz, every time instead of showing this full plane, we may just represent with a half plane. That will be more than enough. Coming to yz, this is the plane of the board or the plane of your paper. So this is a complete plane. We may just show half the plane. Now when I am showing this plane, you have to be little careful whether if I show this, or depending on the molecule, supposing that I show this, both are one and the same. This is a full plane. Out of this plane, if I draw this particular half, or I may draw this half which is towards your left hand side, or I may draw a half which is towards right hand side, or the one which is below, everything will represent that sigma yz only, right? This is representing sigma yz, or I may represent this. So either of these representations can be used. This one or this one or this or this one or also this one. So anything you can use. Same is the case for this. I may also show it this way, or I may show in the full way. It is up to our understanding. It will be easy for you when we take up more number of examples, but these are the three different planes. One is sigma xy, the another one is sigma xz, and the last one is sigma yz. In the beginning class I told you, once we are passing the planes, how the coordinates shift or they exchange with the opposite phase we have seen. Whatever plane that we are passing through, that is taking up two coordinates, and those two coordinates will remain there, whereas the other coordinate will shift its phase. Well, coming to the definition, how should we define a plane of symmetry or a reflection symmetry? This is also an imaginary element. Let me define it. It is that imaginary element. So I'll try to show it with the example molecular model of hydrogen, H2O, hydrogen, hydrogen and oxygen. This is a water molecule. Whatever plane that we are choosing, let me choose it as a xz, xy or a yz plane. It is that imaginary element that bisects the molecule into symmetrical halves. This is a very simple definition. Now when I say that is bisecting the molecule into symmetrical halves, where should the plane pass from? It has to pass through the center of the molecule, which is nothing but the center of gravity of the molecule. So the first thing we have to do is to identify the center of gravity of the molecule. We must have a decent idea of the geometry. Now once I have drawn this H2O, I know that the center of gravity lies with the oxygen. So if at all I am trying to pass a plane, that plane has to pass through the center of gravity. And through imagination, we have to imagine in such a way that this plane is bisecting the molecule into symmetrical halves. We may also call it as equivalent halves. Once it is bisecting the molecule into symmetrical halves, what exactly it does is, it will reflect the halves. So how to imagine it? Let us understand. Suppose that this is H1 and this is H2. 1 is towards your right hand side, 2 is towards your left hand side. Let me pass this plane, which is a xz plane. Now once I have passed a xz plane, this is bisecting the molecule into symmetrical halves. It is passing through the center of the molecule and it is bisecting the molecule into symmetrical halves, where each half is a mirror image of the other. So once I cut this, you just imagine that I am cutting the molecule. Once I cut this, this is the right half and this will be the left half. The left half will reflect in the right half, whereas the right half will reflect in the left. That is a very simple operation to understand. I am just repeating all these points now. Whatever molecule that we choose, plane of symmetry is that element or that imaginary element which pass from the center of gravity of the molecule and bisects the molecule into symmetrical halves that are mirror images to each other. Each half will reflect into another half. This is the definition of plane of symmetry. Once we hold any molecule, we have to simply check how many planes are present. This was one plane that I was showing to you, right? So this is how if I pass a plane that can bisect the molecule into symmetrical halves, where each half is a mirror image of the other. Well, there a question arises. The question is, can I simply say that I am putting a mirror and there is a mirror image of the molecule? Can I say that this is a mirror symmetry, or instead of calling it as a plane of symmetry or reflection symmetry, can I call it as a mirror of symmetry or mirror symmetry? Well, the answer is no, we cannot call it as a mirror symmetry or a mirror of symmetry. The simplest reason being, what is the difference between a mirror and a plane means mirror is real one, whereas the plane is imaginary, and that plane is a symmetry element which is purely imaginary, but mirror, it is a real one. And supposing that if I am holding the molecule, I want its image, then I have to put a mirror which is a real one, I have to put it outside the molecule or the molecular model that we are choosing. We cannot just hold a single molecule, but if at all you want a mirror image, then that mirror is to be kept outside the molecule, then we can have the mirror image of that particular entity, let it be a molecule or any substance. But when it comes to the plane, plane is not kept outside, but it can bisect through the molecule, it can bisect through the center of the molecule, and plane is like a double-sided mirror. So once I am trying to pass it through the molecule, this half will reflect towards your right and your right half will reflect towards your left. So simply speaking, plane is like a double-sided mirror where both halves reflect in the opposite halves, whereas a mirror is real, it has to be kept outside. Once I am taking any mirror, that mirror is real, and we have to keep that mirror outside the molecule or any chemical entity that we choose, right? So this is a difference between a mirror and a plane. Mirror is real, whereas plane is purely imaginary. Plane is like a double-sided mirror where it reflects the two halves in their opposite halves. That is the definition of plane of symmetry and the understanding and the difference between the mirror and a plane. Now to show this, let us start with the water molecule again, which is one of the simplest of the molecules that we can choose. I will also give you some reference point how it changes all those things. So let me start with a water molecule. Hope you are following all the examples, and you have to also work out these examples as and when I complete a particular topic. Right, now I am showing a water molecule. What we do is we are trying to pass a plane which is a XZ plane. So this is the plane that I am trying to pass. We will also check it with some other planes whether they are present or not, but in the beginning let us try to pass an XZ plane. The center of the molecule is with oxygen, so I am passing a plane. This is that plane. So whether I may show only half a plane or a full plane, it is just up to our understanding. Every time for making a full plane, it will be little bit difficult. So for our convenience, we can simply choose half a plane. This particular representation, you have to imagine Hello everyone. In our last classes we have seen the introduction for symmetry. Along with the introduction we have also started the symmetry elements, rotational axis of symmetry, and many examples have been discussed. We have taken some examples where we have shown C2, C3, C4. We went till C6, C7 and C8 example has also been given. We have taken some different examples such as a line and what are the different rotational axes also we have seen. And within this rotational axis, how many different types are there? Principal axis, subsidiary axis, and when should we assign principal axis, when should we assign subsidiary axis, guidelines, all those things we have seen. Two classical examples have been taken. One is BCL3 to show a guideline 1 where the higher order gets a priority. Then we have taken an example of ethylene where the principal axis gets a priority according to the number of atoms through which the axis is passing from. So after seeing all these things, then we will enter into another symmetry element which is called as the plane of symmetry. This is one of the basic symmetry elements, and as I told you, whenever we look at any chemical entity or any substance, the immediate thing that strikes into our minds is the plane, whether it is symmetric with respect to plane or not. We might have seen Taj Mahal in real, or you might have seen any image of it. At a very first instance, we say the construction looks very beautiful and very symmetric. Whether it is beautiful or symmetric, we have to come to some conclusions being a science student, because there is a little bit difference between the beauty and the symmetry. How that goes, I'll just explain, because we have entered into the another symmetry element called as plane of symmetry. So the second symmetry element is called plane of symmetry. This is indicated by sigma. You may also call it as a sigma symmetry. The other name given it is reflection symmetry. In the case of rotational axis of symmetry, we can also simply call it as axis of symmetry, because axis is the symmetry element, whereas rotation is the operation which is carried out around the axis. But both the symmetry element as well as the symmetry operation are intricately related. So they are so intricately related that we take the name of operation within the element or element along with the operation. Therefore, we have told that it is a rotational axis of symmetry, that is an element. Truly speaking, rotation is not an element, it is an operation, but we say rotational axis of symmetry, or you may simply call it as proper axis of symmetry or axis of symmetry. In a similar way, this is referred as a plane of symmetry, where plane is the element, or you may also call it as a reflection symmetry, where reflection is the operation that is being carried out. What exactly is this plane? Now let me just show you. Suppose if I am taking this, you can imagine this to be a plane. Is there any difference between a plane, or can I just call it as a mirror, because there is some reflection? So since there is a reflection, instead of calling this as a plane, can I call it as a mirror? Maybe if I just put it here, can I just call this as a mirror? Let's see. I am just taking a molecule. Suppose that it is a hydrogen. I have taken hydrogen. Mirror, it is a real thing, and every mirror is kept outside the entity that we chose. We cannot hold a single molecule or any single atom, we cannot hold, but just suppose you are holding some substance and you want a reflection of it. then mirror is kept outside that particular substance or outside that particular molecule that we have chosen. So if at all I have a mirror, then I will be holding that mirror and that mirror will be outside. Here will be its reflection. This is being reflected here. If this is 1 and 2, this will be 1 and 2. 1 and 2 will reflect. When it comes to the plane, plane is something which is purely imaginary and it will pass through the molecule. It is just passing through the molecule, and imagination is, its operation is to bisect it. It will bisect or simply cut the molecule into symmetrical halves or equivalent halves, where each half is a mirror image of the other and they reflect in the opposite halves. Definition may look little lengthy, but understanding is very simple. Plane is purely imaginary, it is a symmetry element, and as it passes through the molecule, from the center of the gravity of the molecule, it will bisect the molecule into symmetrical halves, where each half is a mirror image of the other and one half will reflect into the another half. So what will be the resultant finally? The resultant is just as we put a mirror outside. Once you are putting a mirror outside, it is just looking similar, but there are some qualitative differences. As we go on taking some number of molecules, you will come to know how a mirror is different from a plane. But for the beginning introduction, you have to remember that mirror is, it is not imaginary, it is real, and it is kept outside the molecule, whereas the plane is purely imaginary. It can bisect the molecule from the center, and reflection operation is carried out where one half is reflected in the another half. So which half is reflecting into which half? For the basics, I will let you know. With respect to the coordinates, x, y and z, we had three different planes. So if I show this particular plane, this is a xz plane, this one is a yz plane, whereas this is a xy plane. I am just showing it again. This is a xz plane, yz plane and a xy plane. So with respect to these planes, which half they get converted, I mean they get reflected, I will put it here. Let me start with a sigma xy, sigma xz and sigma yz. When I take sigma xy, it is this plane. So when I take xy, whatever half that is above will reflect into the below, and below half will reflect into the above. So the above half will reflect into the below half, and below half will reflect into the above half. This is sigma xy. Sigma xz, right, this is sigma xz. So whichever half is towards your right hand side will reflect in your left, and whatever half that is towards your left hand side will reflect in the right. Right half will reflect into the left, whereas the left half will reflect into the right. This is with respect to sigma xz. When it comes to sigma yz, which is the plane of the board, so once I say the plane of the board, now imagine if this is the plane. Hope you are able to see the colors, or maybe these two colors are very light. Okay, now let me take these colors. a blue color and a magenta or a dark pink color. So one half towards this is a blue. So if I imagine that this is a plane, one half is blue, the other half is a magenta or a pink color. Just imagine that it is a dark pink color. Supposing that if I am, imagine this as a molecule or some chemical entity, I am passing a plane. As I pass a plane, this is a YZ plane. Whatever half that is towards you, that half will reflect away from you, and whichever half was away from you, it will reflect towards you. So as I pass a plane, after the operation, this is what you see. This is only half an operation. So it is just looking similar to the original one, but it is not the same. Then again I pass a plane, this blue is reflecting towards you. So what do we say? Whenever we are passing sigma yz, whichever half is towards you will reflect away from you, and whichever half was away from you will reflect towards you. So these are the exchanges. Whenever we pass xy, top and bottom will exchange. Whenever we pass xz, right and left will exchange. And whenever we are passing xy, top and bottom, xz, right and left, and yz, towards you and away from you half will exchange. So this is with respect to the three planes. Now once you have understood this, then we'll take up some molecules. While starting the plane of symmetry, I said beauty and symmetry, they don't go on a single track. Both are different. Why are they different? Let me give one classical example. I don't know how many of you like the beauty of Taj Mahal. If at all you look at the symmetry, as you pass an imaginary plane, one half is an exact reflection of the another half. So we say that there is a plane of symmetry in the Taj Mahal. Or if you are a resident of Hyderabad, then you might have seen Charminar, where one half is a reflection of the other half. That is merely by passing a plane. So supposing that we have a, now if this is an image of Charminar, just imagine, where we have 4 minars. If I try to pass a plane, one half is a reflection of the another half. Then most of us say that this particular construction is beautiful because of the symmetry that is present in it. How far is it true? Means it is true to a larger extent. I may just choose a butterfly. If at all you look at butterfly, you say it looks very beautiful because one half is a reflection of the other half. You choose most of the animals, or you choose most of the constructions, man-made constructions, or to that extent, just physically you look yourself. As we look ourselves, you can just watch, one half will be the reflection of the other half. If at all you are passing an imaginary plane through me, one half will be the reflection of the other half. But internally it is different. Anyway, internally, anatomically you need not pass it. Only for our illustration purpose we say, just if we can pass an imaginary plane from my image, one half will be like a reflection of the other half. So what scientists have done is, they have done a simple experiment. They were watching all the symmetrical things, and then they were just attributing this beauty of that particular monument or beauty of some particular thing to symmetry. Because most of the scientists were thinking that beauty and symmetry are purely related. Whichever thing that is beautiful has to be symmetrical. That is what they were thinking for several years. Let me give a simple example. Supposing that you have chosen a cockroach or you have seen a cockroach. Well, how many of you like the beauty of the cockroach? That you just answer yourself. Just by looking at a cockroach, I don't know how many people will say, oh, that cockroach is very beautiful. How many people will say, maybe a biologist or a zoologist may say, not all, but maybe some of these zoologists may say that cockroach is very beautiful. But for many, especially girls, whenever they see cockroach, they never say that the cockroach is looking very beautiful. Why is it not looking beautiful? Is it not symmetric? If I try to pass a plane, it looks perfectly symmetric. One half is a reflection of the other. If at all the beauty to any particular thing is imparted because of symmetry, then cockroach, which looks perfectly symmetric by passing a plane of symmetry, should also look beautiful. But very rarely do you listen the term that cockroach is looking very beautiful, very rare. Now here is a point where you can say that beauty and symmetry need not be related directly. There is an indirect relation. Most of the symmetrical things look beautiful anyway, but all things which are symmetric need not be beautiful. One good example is here. Anyway, this is for our explanation purpose that I give the example of cockroach. But scientists, they just do not sit quietly. They always want some invention or discovery to be done. Maybe I am not very good at drawing, but what scientists have done is they were looking at many women who were looking more beautiful. They have taken some Miss World or Miss Universe. They have taken the images of all these Miss Worlds and Miss Universes, and what they have done is, if at all the beauty, whichever women or whichever girl that is beautiful, is it just due to symmetry or not, they wanted to test. So what they have done is they have taken the image of those Miss Worlds or Miss Universes, and what they have done, they have passed imaginary planes. And once you pass an imaginary plane, with this you can also do it in the Photoshop if required. This is one half, this is the other half. Now once I get a right half, this is the right part of the face, the left part of the face. So once they got the right part and the left part of the face, what they have done is they have reflected the right part of her face and left part of her face, and this right part. So once they have taken the halves, then they have done the reflections. 99% of the times, whatever images that have been created through the reflection of the halves do not look beautiful. Instead, most of the times they look even ugly. You will not be ready to see your own image once you do the bisection of the photo image and do the reflection of the halves. These halves do not exactly look like the original one. Now this clearly say that the two halves are not perfectly symmetric. So whatever beauty that is being imparted to her particular face is not due to symmetry. So the final conclusion was, beauty is in our perception. How we perceive a particular thing, beauty depends on it. Whereas symmetry, whether you perceive it properly or perceive it improperly, it is up to you. But symmetry, once if it is present, it do not change. This board is looking like a perfect rectangle. Whether you like it or not, it is a rectangle. It is symmetric. You may like it or not. But when it comes to the beauty, it is how you perceive it. Anyway, this is a simple example that I wanted to tell you, that symmetry and beauty are not directly related, but most of the symmetrical things look beautiful anyway. After the brief introduction of plane of symmetry or reflection symmetry. We'll try to show it by taking a simple molecule called as a H2O or a water molecule. First let me draw the water molecule, and whatever plane that I am going to represent, I will not represent a full plane because this is only for our understanding. Imagine that I have to pass an exact plane. Every time I will not draw exact plane in this way. It will not be a full plane. Just for our convenience, I will only draw half a plane. That should do the job. Supposing if I have to draw a plane in the water molecule, so this is the exact plane in full. If the same thing has to be represented in half, this is how we represent. And that looks much convenient, and also it is giving you more information. In this way it looks like oxygen will fall within the plane, but this plane is whether bisecting the oxygen or not, full information will not be coming from this diagram. In this diagram we can simply imagine, okay, it is passing through the center of the oxygen, and even the oxygen is being bisected. That is information that we are getting from the half a plane. So for my representations I will be going with the half planes, which are much convenient for us. The operation that we are carrying out is a sigma. This is a xz with respect to the beginning conventions that we have taken. Now if it is an xz, which halves must exchange means the right half and the left half will exchange. Forget about the above and below half, towards you half and away from you half, you just forget about it. It is the right and the left halves that will exchange. Now as they exchange, the imagination should be in such a way that I am passing a plane that has bisected the molecule into symmetrical halves. Bisected means cutting. So you are getting one half to this end, other half to this end, and whatever half was coming towards your right hand side, that gets reflected in your left hand side, and whichever half that you are getting in your left hand side will be reflected in the right hand side. In such a case, H1 should reflect at H2 position and H2 reflect in H1 position. So we say that H1 and H2 are exchanging, they are reflecting into one another. Upon reflection anyway, in some books you might have seen two in this manner, and one would be reflecting. So if it is 2, that 2, yeah, that 2 would be reflecting here. If I put such a representation, you may get confused, so you need not go with such a representation. This is more than enough for us to understand. If I choose a reference, H1 is towards your right hand side, that is being replaced by H2. If I don't label them as 1 and 2, the molecule simply looks the same, HOH, HOH. But if at all I start labeling them, then the two structures are not the same, they look similar, the position of the atoms is being changed. Therefore, whatever structure that we got here, it is not the identical to the original one, instead it is an equivalent one. This, let me put it as 1, that is 2, and this is 1. The first one is the original structure, the second one is the equivalent structure or the equivalent configuration of the first. Since it is not identical, let me pass one more plane, and we have to pass planes to such an extent where we get a identical structure. I am passing one more xz. again the operation is the same. Supposing that if I am passing this plane, whichever half is towards your right will reflect in the left. So H2 now will reflect in your left hand portion, H1 will reflect towards your right hand portion. That third structure is looking identical to the original one, then you have to stop the operation, because we have to do the operation until we get an identical structure or identical configuration. I got an identical configuration, therefore I am stopping this. Now after looking at these structures, you may just try to answer a simple question. H1 and H2 are being exchanged, or they are being reflected into one another. Does the oxygen shift, or does the oxygen exchange with any other atom, or is it changing its position? In rotation, what we have seen is, as I rotate, suppose if the rotational axis is passing through oxygen, if it is passing through the oxygen, even the oxygen is rotating, but that is rotating within itself. So whichever half was towards you, as I rotate, that half is moving away from you. That is with respect to rotation. In the case of reflection, is there any change within the oxygen, or only the hydrogen atoms are exchanging with one another? You just think for a while. And whenever I ask such questions, my sincere request is, you just pause the video, you try to answer the question, and then you check for the answer, which I am going to tell now. Once I am passing a plane which is passing from the center of gravity of that molecule, which is in the center of oxygen, within the oxygen also there is one half towards your right, the other half towards your left. So as I pass a plane, the one half which is towards your right, I am putting it in lines. This particular half will reflect here, and once again I pass a plane, this will reflect here. So whatever half that was towards your right hand side in the lines, again that has come towards your right hand side. So that is how you have to understand the plane. It is an in-depth understanding. It is not like simply I have passed a plane, hydrogen atoms have been exchanged. You have to also see whether there is any change within the atom through which the plane is passing. The answer is yes. Within that particular atom, there is also a reflection. One half is being reflected into the other half. This is one understanding. Second understanding, all these are little bit deeper understandings, because once you become lecturers, we require a deeper understanding, or even in your research field we require such a exploration. If I am putting plus, plus indicates that half which is towards you. This is for our convenience. Minus indicate the half away from you. So as I am passing a plane, now as I pass a plane, whichever half that is towards you is reflecting, again it is towards you, but in your left hand side, and left part will reflect in the right, but plus will remain plus only. It is just like this. If this is one half, it is reflecting as this way only. It will not reflect this way. That is the difference. Hope you are getting it. If this is a plus which is towards you, that will be plus reflecting, but it will not reflect as minus. This it will not do. So we got a plus. Now as it is reflecting, it is just reflecting as plus only. So if at all I am putting my hand here, right hand, after passing a plane, this one is reflecting it this way. It is not reflecting this way. There is a qualitative difference. Why I am showing all these things? And as I pass another plane, that has come to its reference point. Even in the rotation we have taken such reference points. We have seen after the full rotations whether we are getting the same reference point or not. So we got that same reference point. We can stop the operation. Once I passed a plane one time, I am getting an equivalent configuration, and as I pass it for the second time, I am getting an identical configuration. There I stopped. This is one plane. Now what I will do is, let me take the same water molecule. Instead of sigma xz, let me change the plane. Let me change the plane as yz, the plane of the board. How many operations we have to perform, we will try to check. Whether we are getting only 3 structures or many, we will try to check. So when I am passing sigma yz, it is the plane of the board. This is how I am passing the plane. In the previous case, this was xz, but now this is the plane, yz plane. So how should we draw that yz plane? I am only just taking the half. In other books you may see a full plane, which is not required. It is just for our understanding. Now as I am passing this plane, what is happening to the position of the atoms, you can check. This is a water molecule. Now I am passing this particular plane. So this is the imaginary plane. As I am passing this plane, what is happening? Where is the position of oxygen? It is not exchanging with any other atom. H1 is also not exchanging, H2 is also not exchanging. Had it been this plane, 1 and 2 are exchanging. But if it is this plane, since that plane is passing through these 3 atoms, those 3 atoms will shift. They will remain there itself, they will not shift. They are just not going to shift. So I have to put 1 here as well as 2 here. Because in the beginning I told you, from whichever coordinate the plane passed from, those coordinates do not shift. In a similar way, from whichever atoms the plane passed from, those atoms will not shift, those atoms will not exchange, right? Now once I have done this, I got a structure which is looking same as the original one. It is not similar, remember, it is looking same as the original one. One is towards your right hand side, one is towards your right hand side. Now should I go for another operation, or I can simply stop here? For xz we have seen 2 operations, then we got identical structure. Can I conclude that for yz there is single operation, only one plane is required because I am getting a identical structure. A second plane is not required because it is like a repetition. I do not want any repetitions in symmetry. We have to go only to that point where we get an identical configuration. So let me stop here because I got an identical configuration. Is it okay? Now if I go by that convention, I will be wrong. As I explained you the plane of symmetry, I was very particular about the halves. Also I said, once it is passing through any atom, that atom will not exchange with any other atom, but within that atom there is a shift. Within that atom there is a shift. How to understand this? Now let us see. I am just taking lines so that this is one half towards you. Imagine this is H2O, HOH. Whatever half that is towards you is with lines, and whichever half is away from you, just imagine it is plain, there is no line. As I am passing this, whatever half that is towards you will reflect away from you. So in the beginning I told you, as I pass yz, towards you half will reflect in the away half. Away half will reflect towards you. Within this, let me take a plus. Within this, let me take a plus. And even in oxygen, let us take a plus. Plus, plus, plus means these are the half that are towards you. After the reflection, the away half will be reflecting towards you. So whichever half is towards me, that will reflect towards you. Now compare both the structures. Are they identical? If you don't take any such reference, and when you put that structure, you will end up saying that this is an identical structure because 1 is at the position of 1, 2 is at the position of 2, oxygen is also at its position. I did not operate, I got an identical structure, but such a convention is wrong. You have to take the references, then you should understand a point that as I am passing a YZ plane, whichever half is towards you will reflect away from you, and whichever is away from you will reflect towards you. So that away half is reflecting towards you, which is being given as a reference of minus. Minus is away half, plus is towards you half. So whatever structure that I got, it is only an equivalent structure because I am having a half which was away. Now let me pass one more plane. So once I pass a plane for the second time, whichever half that was towards you now will reflect away from you. So this is what you get. Minus is now towards you. As I pass the plane, that half will reflect away from you, and away half is coming towards you. So you got the first structure configuration. Now you can stop at this point. So this is a sigma yz. Hope you understood this point. I am stressing a lot on this particular thing. This might be looking very simple for some students, but for most who don't understand the symmetry basics, here you can get those basics. For a plane or for a rotation, it is always good that you take some reference, and even for that particular atom which looks unmoved or unshifted with respect to plane, if you take the proper reference, even every atom there is a shift, whether it is rotation or whether it is reflection. You can see that every atom has a shift within itself. If this is H1, as I am passing a plane, the away half will reflect towards you. H2, away half will reflect towards you. Oxygen, away half will reflect towards you. Though the position of the atoms is not being exchanged, but within the atom there is a shift, and such a shift you have to understand. So just to give such a reference, I have taken plus, which is towards you. As I pass yz, that is going away from you, and away half is coming towards you. We have taken it in the minus reference. Finally, I am passing the plane for a second time. That away half now is projecting towards you. So I have taken it as a plus. So this is how we have to understand plane of symmetry at a deeper level. Right, we have seen two different planes. The first one, in the previous example, it was a xz plane where 1 and 2 were getting exchanged. Now this is a yz plane. In the yz plane, towards you half is exchanging with the away half. Suppose if I take xy plane, let us see whether it is present or not. Let me take xy plane, and once I pass that xy plane, we have to just see whether it is valid or not. So once I pass this plane, that reflection will be this way. Below half will reflect in the above half. Then whatever structure that we get, we have to compare it with the original one. Is it equivalent or not? We have to check. In the first example, the both hydrogens were below. With respect to this plane, they were below. Now as I pass an xy plane, they are reflecting above. So these two structures are not at all equivalent pair. For that reason, we say that sigma xy in case of water molecule is absent. This plane is absent. This plane is present, xz, yz is also present. Conclusion is water molecule has two planes, and these two planes are different. They are not the same, they are different. One plane is able to exchange H1 into H2, whereas the other plane is not exchanging any atom, though there is a shift within every atom which is not told every time. Just like whatever molecule you choose, there is a C1 in it. Every time we did not say. In a similar way, from whichever atom the plane pass from, even that atom will have a shift within itself. This is with respect to a simple molecule called water. Now let me choose one more molecule, ammonia. This is how I am holding the molecule for ammonia. The one that I am holding, you just imagine it as a lone pair, and these are the three hydrogens, 1, 2 and 3, the central atom being the nitrogen. You may hold the ammonia in this manner, or you may also hold it in this way. So as I am holding it in this way, you can check. The three hydrogens are facing towards you. Lone pair is away from you, or you may also hold it this way, where the lone pair is towards you, three hydrogens are away from you. This is a much convenient position. Instead of holding this way, you may hold it this way. So for showing the planes, nitrogen, every time representing the lone pair is not required for the molecules. You need not represent the lone pair. It is understood. Depending on the excess or deficiency of the electrons, it is understood that you need not represent any lone pair. It is just like a skeletal diagram in your organic chemistry. Whenever I put, say, some structure like this, I need not say that there are 6 carbons and 6 hydrogens. It is understood. In a similar way, I need not put any lone pair. It is understood that within ammonia there is a lone pair over nitrogen. How to represent the planes? Now in this case, if you can very carefully look at the nitrogen attached to 3 hydrogens, one hydrogen is in the plane of the boat, one hydrogen is coming towards you, and one hydrogen is like away from you, right? So how many planes are present means, I am showing it here. Supposing if I am holding the molecule in this way, okay, so this is how the molecule has been drawn. One hydrogen is in the plane of the boat, one is projecting towards you, and one hydrogen is away from you. How to show the planes means, so for your convenience, let me hold it in this manner, right? Let me pass a plane from here. I am just trying to pass a plane from here. These are 120 degrees separated molecules. So I just cannot take xz, yz and all those planes. You have to go with the planes in such a way that whether it is present within the molecule or not, you have to check. Now you are just coming to a little bit higher stages. Forget about only xz, yz or xy planes. You have to check for many other planes also. If at all I am passing this particular plane, which is a plane passing through one of the hydrogens and the nitrogen, right? Now as I pass this plane, whichever half that is towards your right hand side, looks exactly the same as another half which is towards your left hand side. So it is bisecting the molecule into symmetrical halves, and these halves are like mirror images to the other. Right is the mirror image of left, left is the mirror image of the right. This is how you are looking at the ammonia molecule if at all I am passing a plane. Which plane is valid means only that plane is valid which will give you symmetrical halves that reflect into one another. So this is a plane which is a valid plane. Okay. On board, it is better to represent it in this way. Very convenient to see. So where is the plane passing from? It is this plane which is like towards you. As I pass this plane, it is just passing, and as it passes you can check one half is a reflection of the other half. It is perfectly symmetric. There is one plane which is present. Okay. Now the three hydrogens are equidistant, all are identical, there is a triangular relation between them. If I am able to pass a plane from H1 and a nitrogen, since there is a triangular relation of identical atoms, I should also be able to pass another plane from H2 and nitrogen, because this should also give you an equivalent configuration. This half is a mirror image of the other half. Likewise, I should also be able to pass a plane from H3 and a nitrogen, because one half is a reflection of the other half. Logic is very simple. Since these three atoms are identical and they have a triangular relation, if I am able to pass a plane from H1 and nitrogen, I should also be able to pass from H2 and H3. So with this logic, we will try to check what are the rotational axis, what are the planes that are present, not rotational axis, what are the planes that are present. So I am not taking this representation, this or this representation, where all the hydrogens are facing towards you. Where is the plane? Each plane is passing from the central atom as well as one of the hydrogens. So I am representing one particular plane. Now I am not naming it as a sigma xz, sigma yz or sigma xy, because these are not with respect to the coordinates. There is a 120 degree angle, not a 90 degree angle, so forget about it. It is not sigma xz, sigma yz or sigma xy, simply I am representing it as a plane. As I pass that plane, whatever half is towards your right hand side, because this is how you are looking at it, this half will reflect in the another half. H1 is not exchanging with any other atom because it is in the plane, so H1 will be here itself, but within a hydrogen there will be an exchange. One half will exchange with the another half, so one should be here as per our understanding. But once you have understood, you need not put one here, you can just represent one there itself. Whereas 2 will reflect in 3, 3 will reflect in 2. Now whatever structure that you are getting it here, this particular structure and the first one, they are not identical. Since 2 is towards your right hand side, that is being replaced by 3. So let me pass one more plane. As I pass this, H1 remain there within itself, though there is a reflection. 2 and 3 are getting exchanged again. So 2 has come to its position, 3 has come to its position, 1 is at its position. What configuration that we got is an identical configuration. There you can stop. How many planes that we have passed? Again the answer is 2 planes. At first plane we got an equivalent configuration, at a second plane we got an identical configuration. Coming to the next point. As I told you, once I am able to pass a plane from H1, I should also be able to pass a plane from H2. So once I pass a plane from H2, which I am not going to represent for each and every structure, with this you should be doing as an assignment. I am telling you what will happen. Simply I have to put it on a paper. If I pass it from H2, 1 and 3 will reflect. So for the first time 1 will be in the position of 3, 3 will be in the position of 1. Pass it for a second time, again 1 and 3 will come to their original positions. So this is a second plane passing from H2. Then we have a third plane. The third plane is passing from H3. When it is passing from H3, H3 will remain at its position. These halves only will reflect, but H3 is here itself. Whereas 1 will reflect into 2, 2 will reflect into 1. Do it for a second time, they will come to their original positions. Okay. So altogether we have 3 planes. One which is passing from H1 and nitrogen, other which is passing from H2 and nitrogen, and third which is passing from H3 and nitrogen. So the conclusion is ammonia has 3 different planes. Each plane is passing from the central atom nitrogen and taking one hydrogen at a time. Water molecule was having 2 planes. Ammonia has 3 planes. Altogether we have 3 different planes within ammonia, 1, 2 and 3. That is the complete representation of the planes. After the examples of H2O and ammonia, let us take up one more example of BCl3. It is a planar molecule. Well, when we look at the BCl3, how many planes do you visualize in the beginning? You look at the molecule carefully. BCl3, try to imagine the planes. Later I am showing you with the molecular model. The central brown colored one is considered to be the boron, and you just consider these whites to be the chlorines, Cl1, 2 and 3 as a clockwise manner. Supposing that if I am holding the molecule in a YZ plane, in the plane of the board, and let me pass a plane. So whether if I pass a plane this way or I pass it this way, this is YZ plane only, you need not get confused. With respect to YZ, if I show this plane, it is a YZ plane, or if I show this way, this is also YZ. The only thing is how we see is differing, whether this or whether this is a YZ plane only. This is a XZ plane. So XZ plane, I may show it in this way, or I may also show it in this way. This is XZ, XZ. This is YZ or YZ, and this is XY plane or XY plane. So any way I may show it, this way or this way I can show it. Why am I showing in two different ways? Because every plane is taking up two coordinates. So with respect to one coordinate and a second coordinate, we are showing it. So I may show it this way, they are same. Now if this is that BCl3, I am passing a YZ plane. As I am passing the YZ plane, this BCl3 is planar molecule. So this particular plane is passing through every atom of this molecule. As it passes through every atom of the molecule, this is how it is passing. Whichever half is towards you will reflect away from you, and away half will reflect towards you. Every time I will not be drawing the equivalent and the identical structures, you should be able to understand by this time. This is just similar to H2O. H2O, right, I am just showing H2O. This is that YZ plane. As I pass the YZ plane, towards you half will reflect away from you. Likewise, you have to imagine the same in BCl3. Only changes in water molecule, hydrogen, oxygen, hydrogen. Here you have an additional atom. This is a chlorine, chlorine and a chlorine. That oxygen is now replaced by a boron. So I am just drawing that structure. We are passing a sigma. How should I show that sigma? That depends. You may draw this half, or from here you may draw, or from here, or from the top. One and two, they are not identical. Towards you half is reflecting away. Suppose if I take reference of plus, which is towards you, will reflect away, and away will reflect towards you, therefore it is a minus. Position of the atom is not shifting, but within itself there is a reflection. Within itself, within the chlorine there is a reflection, within the chlorine there is a reflection, and within the boron there is a reflection. So both these structures are not identical. Then let me pass one more plane. This will give you identical configuration. This is with respect to BCl3. There is a plane which is passing from every atom of the molecule. By definition, we can call this plane as a molecular plane. What is a molecular plane means? This is a plane that bisects all atoms of the molecule. Such a plane is referred as a molecular plane. Apart from this, if you can visualize any other plane, you can just go through. I have drawn the molecule. Is there any other plane that can bisect the molecule into symmetrical halves? It is like trial and error method. Every time you have to imagine BCl3, try to pass any plane that you like. The only requirement is that particular plane should bisect BCl3 into symmetrical halves. Again I am holding the molecule. Now as I hold the molecule, you can just check it. This was the plane. Towards you half was reflecting away from you. After this, now let me pass one more plane like this. It is passing from a boron and one of the chlorines. So as I pass this plane from boron and one of the chlorines, I am holding it away from you so that you can see the model clearly. Right half is reflecting in the left half. This particular plane that is passing from boron and chlorine is bisecting the molecule into symmetrical halves, where each half is a mirror image of the other. Again, this is similar to the H2O1, sigma YZ kind of a plane. Only difference is we have one more chlorine here. If you can look it carefully, these three are chlorines. They have a triangular relation, they are equidistant. It is a perfect equilateral triangle. If the distances had been different, then maybe all planes will be present or not, we have to check. But logic goes this way. All the three chlorines are identical, all are say single bonded. Now once they are single bonded and identical, they are equidistant. Once they are equidistant, if I am able to pass a plane from one of the chlorines and boron, there will be another plane from a second chlorine and a boron, third chlorine and a boron, similar to ammonia. Not the same, but similar to ammonia. In ammonia, there was each plane passing from a hydrogen and a nitrogen. In this case, each plane is passing from a chlorine, boron, chlorine, boron, chlorine and a boron. Since this is a planar one, you also have a fourth plane. In ammonia, such a fourth plane was absent. This is plane 1. Plane 2. And a plane 3. Along with these three planes, we also had a molecular plane. Right? To differentiate between ammonia and BCl3, in ammonia we had 3 planes, whereas in BCl3 we are having 4 planes. One plane is a molecular plane that is bisecting all the atoms of the molecule. Along with that, we also have these 3. Let me take ethylene. Choose an example of ethylene. Now this is an ethylene. Try to visualize how many planes are present in this. You may hold any way as per your convenience. The general representation we take is this. This is just by convention. Now let me draw the structure. Try to identify how many planes are present in it. Let me take H1, H2, H3 and H4. So at the first instance of the molecule, Ethylene is a planar molecule. So, for every planar molecule there will be a plane that is called as a molecular plane. Here also there is a molecular plane. I may represent it from here, 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 or from here. It is like a YZ plane, right. This is plane 1. Now, if I can pass this plane, you can just watch. If I am passing this plane, one half towards your right will reflect into your left, because both halves are looking symmetric. Such a plane is present and it is valid. First plane, second plane. Apart from this, do you find any other plane? Well, this is a classical example for the presence of sigma xy, xz as well as yz planes. First, let us start with xy plane. Now, this is the xy plane. As I am passing this xy plane, above half is a symmetric half to the below one, or above half will reflect into the below. Both are symmetric. Let me pass a xz plane. Right half will reflect into left. Now, let me pass a yz plane. Towards you half will reflect away from you, right. So, there are 3 different planes in this. Let us represent all these 3 planes with some structures. Ethylene is very important because it is also asked with reference to the group theory. So, you must understand it very carefully, how the atoms are being shifted, what kind of symmetry elements are present in them. In the first case, let me start with a sigma xy. It is possible to represent the planes as xy, xz and yz. Wherever it is possible, we will try to represent. If it is not possible, we will simply put it as a sigma. That is more than enough for us. The next one, let us show a sigma xz. And the third one, sigma yz, which is the plane of the board. All these are, now this is planes. One is sigma xy, sigma xz and sigma yz. What are the position of the atoms? We will see. Look at the first one, xy. When we are passing xy, above will reflect into the below. So, 1 and 2, 3 and 4 they get exchanged, 1 with 2, 3 with 4. 1 comes here, 2, 3 and 4. That is for the first one. Second one, right half will reflect with the left half. So, first 1 and 4 will reflect into one another. In the second case, 2 and 3 will reflect. In the third case, towards you half will reflect away from you. This is how it is happening. 1, 2, 3, 4, 1, 2, 3, 4. But what is the difference? You can understand only by taking a reference. So, that reference is, suppose if I put plus towards you, here that become minus, that is moving away from you. If you do not take such a reference, then both structures look the same. In fact, they are not the same. In the beginning, you will find this difficulty, but as you practice more and more examples, you will find that by passing one plane you will never end up with an identical structure. Definitely you have to pass a second plane to get an identical structure, whatever plane that you choose, whatever molecule that you take. If a plane is present, then two planes will bring the molecule into identical configuration. Now what we find is a equivalent configuration, so I am trying to pass one more plane. When we pass a second plane, the structure that we get is an identical structure. We refer it as identical structure, identical configuration, identical orientation. They mean one and the same. We just exchange the term configuration with orientation with structure, etc. This is how we have to take the planes. In the first case, we will try to check. Suppose if I am passing this plane, above half is just reflecting below. Now when the above half is reflecting below, the question is the away half coming towards you? Is the away half coming towards you? That is the question. Just as here we have seen, suppose if I take a plus which is towards you half, as I pass a plane that is moving away from you, so that is becoming minus, and I pass another plane that will reflect towards you, that is fine. In this case, if I take a plus, as it is reflecting, does it become minus? Next, if I take a plus, as I reflect, when it is reflecting here, does it become minus? You just think for a while, pause the video and then you just think for a while. In this case, plus is becoming minus. When you pass a second plane, minus is becoming a plus. So should it be the same for each and every plane, for each and every molecule that you are passing? Check for yourself. Now here is how I am showing it. In the first case, the above half is just reflecting this way. It is not reflecting this way. So if it is plus, plus will reflect as plus. In the second case, if this is plus, once I pass a plane, this will reflect as plus only. Whereas in the third case, now if this is plus, as I am passing a plane, this will reflect as minus. You pass a plane again, it will reflect as plus. So that particular reference is changing. Please keep it in mind. In the first two cases, that reference point plus and plus is remaining. Plus is just reflecting as plus. Plus is just reflecting as plus. Whereas in this case, plus is becoming minus. Because when we come to inversion, that inversion is completely different. When we are discussing about the inversion and how it goes, that is different. For it to understand, you should be having an idea of all these things. If you don't get into much deeper, it is just very easy to understand. You take ethylene, pass a plane, shift the atoms, you get an equivalent configuration or equivalent orientation. Then you do it for the second time, you will definitely get an identical configuration. So you need not take the references, but that will give you a better understanding of it. Okay, this is for the case of ethylene. How many molecular planes are present? Answer is 1. For every planar molecule, you will definitely have one plane. Right. When we were discussing about the rotational axis of symmetry or simply proper axis of symmetry, whenever there is more than one rotational axis, then we have done some separation. One was called as a principal axis, the other was called as a secondary, subsidiary or auxiliary axis. Likewise, within the molecule, if there is only one plane, then you may simply call it as the presence of a plane. Suppose if the molecule has more than one plane, is there any need to differentiate them, or is there any need to label them? The answer is definitely yes. Once you have more than one rotational axis, we have differentiated them. Likewise, once we have more than one planes, we will also try to differentiate them. Based on this, once I say that we are trying to differentiate them, there must be some basis. What is that basis? In the case of rotational axis, it was the fold, higher fold, principal axis, lower fold, secondary axis. Or if you choose ethylene kind of molecules, the one that is passing from more number of atoms is the principal, and the one that passes from less number of atoms is the subsidiary. Whereas to differentiate the planes, it is not how many atoms it is passing through. Instead, it is a different one. We have three different planes. The first one is called as a vertical plane, horizontal plane, and the third one is a dihedral plane. Vertical plane is represented by sigma v. Horizontal plane is represented by sigma h. Sigma and a lowercase letter or a small letter, small v, small h. It should be like a subscript. Dihedral plane is represented by sigma d, small d, as a subscript. This is how we show sigma v, sigma h and sigma d. How do you define a vertical plane as, or how do you define a horizontal plane or a dihedral plane? All this is with reference to some rotational axis, and that rotational axis that we will be choosing is a principal axis. In this case, we will try to take C2, then we will be able to define it. In the case of BCl3, we have a C3 which is a principal axis, and we have three C2s that are subsidiary or secondary. With respect to the principal axis, suppose if there is any plane which is parallel to the principal axis, any plane that is parallel to the principal axis is called as a vertical plane. I am just repeating the point. Any plane which is just parallel or along the principal axis is called as a sigma v, vertical plane, and any plane which is perpendicular to the principal axis is called as horizontal plane. These 2 points are very important, you just differentiate them. Any plane which is parallel to the principal axis is a vertical plane. Any plane which is perpendicular to the principal axis is a horizontal plane. Okay. Here just let me give you one important notice. Notice that suppose if I ask this, what is this plane? With reference to you, you may just answer yourself, what is this plane and what is this plane? So the immediate answer I get is this is a vertical plane, this one is a horizontal plane. But what is the reference for this? There must be some reference. When do I say that this is vertical and when do I say this is horizontal? That is with respect to me. Supposing that if I am standing, then with respect to my posture, I say this is vertical, this is horizontal. Supposing that I am sleeping, or suppose that you are sleeping, and as you sleep, you ask yourself what is the vertical plane. As you sleep, then you will say this is the vertical plane. But for a person who is standing, your vertical will become their horizontal. Suppose if you are sleeping this way and you are showing this as vertical with respect to you. A person who is standing, to him or to her, this looks like a sigma h. So for showing all these planes, there must be some reference point, and that reference is we ourselves. If I am standing, this is vertical, this is horizontal if I show. But when it comes to the molecules, don't ever think that if I show it this way vertical plane, if I show it this way horizontal plane. Forget about this convention. You just come to a convention where we have to follow the principal axis only. If the principal axis is in this direction, if the plane is parallel to it, this is a vertical plane. If the principal axis I am holding is in this direction, I am passing a plane. Now don't call this as a sigma h. It is not a horizontal plane. It is not with reference to you. It is with reference to the principal axis that we are choosing. Right? So if this is the principal axis, if that plane is parallel to it, you simply call it as a vertical plane. If I am showing it this way, this is also parallel to it, vertical plane. I am showing it this way, this is also parallel to it, vertical plane. This is perpendicular. So this becomes a horizontal plane. I hold it this way, this becomes horizontal. Plane is the same, but the way that we are looking at it is different. I show it this way, horizontal plane. Show it this way, horizontal plane, because perpendicular to the principal axis. Perpendicular to the principal axis. I show it this way, parallel to the principal axis. Parallel to the principal axis. Parallel to the principal axis. Parallel. Parallel. So don't get confused in which way I am showing it. Only thing is whether it is parallel to it or not, you have to check. Okay? And whether it is perpendicular to it or not, you have to check. If it is parallel, make it as a sigma b. If it is perpendicular with respect to the principal axis, make it as sigma h. Sigma b, sigma h differentiation with respect to the principal axis. Plane which is parallel to the principal axis, that is sigma b. And plane that is perpendicular to the principal axis is sigma h. That is how you can differentiate sigma b with sigma h. When it comes to the dihedral plane, this is a particular plane which is little bit different from a vertical plane and a horizontal plane. Here we don't take the reference of a principal axis directly. Instead we say it is with respect to C2. This is also with respect to a rotational axis, but not a principal axis, but it is with respect to a C2. How it is related to C2, I will tell you. If any question is asked what is a dihedral plane, the simplest answer is it is a plane that bisects the dihedral angle. Right? What is a dihedral plane means? It is a plane that bisects the dihedral angle. Then the question appears, what is a dihedral angle in this case? This dihedral angle is that angle which is subtended between, these are little bit mathematical terms, subtended between two similar consecutive C2s. Two terms are being introduced. Dihedral angle is an angle subtended between two similar, they have to be similar, consecutive, one after the other, two similar consecutive C2s. right? Suppose if I am having a C2 in one particular molecule, I am having another C2. These two C2s are similar. Then there is an angle between them. That angle is called as a dihedral angle, and any plane that bisects this dihedral angle should be called as a dihedral plane. It is that simple. We will take some examples, then it will become easy for you to understand. This is only by definition. A plane parallel to the principal axis is a vertical plane. A plane which is perpendicular with respect to the principal axis is called as a horizontal plane, whereas a plane that bisects the dihedral angle is called as a dihedral plane, and dihedral angle is made, or it is subtended between two similar consecutive C2s. Now let us get back to the examples. I have taken a water molecule. How 1 and 2 are getting exchanged, that is not our priority, but whatever planes that we have represented, we must be able to label them, whether it is a sigma V, sigma H or sigma D. Let us put the principal axis. There is only one axis which we are calling it as a principal axis. This is the principal axis. By convention, we are taking a clockwise rotation. Now in the first case, this is the principal axis. With respect to this principal axis, whatever plane that we are passing is parallel to it. This is parallel to it. So this particular plane must be called as a sigma V vertical plane because it is parallel. In the second case, still this is the principal axis, but the plane that we are passing is a YZ plane. This plane is also parallel to it. It is not perpendicular. It is not an XY. This is parallel, or I show it this way, it is also parallel. So this is parallel, this one is also parallel. What is our conclusion? The first plane, previously we have simply called it as a plane. We did not differentiate them. Now let us differentiate. This particular plane is called as a sigma V. Right? In the previous case, what we have told is one is XZ, one is YZ. There is no XY, but according to some other definition, this will become a sigma V. What will this become? This is also parallel, so make it a sigma V. Right? Make it a sigma V. You may not be able to see pink color. That is a sigma V vertical plane, right? What do we conclude now? In water molecule there are two planes and both the planes are vertical planes. This labeling is with respect to the principal axis. When it comes to ammonia, you have three planes. How many of these are vertical? How many of these are horizontal? And how many of these are dihedral? Well, in nitrogen, there is a C3. And where is the C3 passing from? This is the rotational axis that is pointing towards you. So this is the first plane passing from H1 and nitrogen. It is parallel to the principal axis. Hence this should be called as a vertical plane. Second plane, I am showing it this way. This is the second plane that is passing through the hydrogen and nitrogen. It is also parallel. This is also parallel to the principal axis. Third one, it is passing through hydrogen 3 and nitrogen. This is also parallel to the principal axis. So this plane, I am calling it as a sigma V. This one is also sigma V. The basis is our principal axis. All the three planes are parallel to the principal axis. Therefore, I am calling them as sigma V. Let us come to BCl3. In the case of BCl3, the principal axis is a C3 pointing towards you, and a plane which is parallel to it should be a sigma V. So a plane that was passing from a Cl1, this is parallel to the principal axis, that principal axis is pointing towards you, hence this becomes sigma V. This is also sigma V, parallel to the principal axis. This is also parallel to the principal axis. All these three planes become sigma V. We have a molecular plane that is passing from every atom of the molecule. It is passing from every atom of the molecule. But this particular molecular plane is perpendicular to the principal axis. This is the principal axis and this is the plane. Since it is perpendicular to it, any way you show, if I draw it from here, it is this way, or it is from this way. Anyway, it is perpendicular to the principal axis. Since this is perpendicular to the principal axis, the molecular plane in the case of BCl3 is a sigma H. The molecular plane in the case of BCl3 is a sigma H. In the case of water molecule, what is the molecular plane? This is the molecular plane. That molecular plane was also a sigma V. This is your rotational axis. This is one plane, a second plane. First plane is parallel to the principal axis. Second plane, which is a molecular plane, is also parallel to the principal axis. So both planes are called as a sigma V. So don't jump into conclusions that molecular plane has to be horizontal plane always. That molecular plane could be a sigma V, or that molecular plane could be a sigma H. Simply molecular plane is a plane that bisects all the atoms that are present within the molecule. Don't get confused with sigma H or sigma V. Don't assign sigma H or sigma V to a molecular plane. In the case of ethylene, that rotational axis that is passing from more number of atoms can be identified as a principal axis. For group theory considerations, that will change, but this is for symmetry purpose. Let me consider this as a principal axis. Once this is the principal axis, any plane which is parallel to it should be sigma V. Now let me pass a plane. I am passing this plane, which is a sigma xy plane. If I pass a sigma xy plane which is parallel to the principal axis, therefore this sigma xy, now we are calling it as a sigma V. Then let me pass a molecular plane. We are passing a molecular plane. This molecular plane is parallel to the principal axis. So it was previously called as a sigma yz. Now we are calling it as a sigma V only. Sigma V, parallel. sigma b parallel to the principal axis. Now I am taking this perpendicular with respect to the principal axis. Since it is perpendicular, previously we called it as sigma xz. Now we are redefining it, and after redefinition we are calling it as a sigma h. Right? There are two sigma v's, there is a sigma h. In this case the molecular plane is a vertical plane. In case of water molecule it is a vertical plane. In case of BCl3 it is a horizontal plane. So don't try to correlate molecular plane to sigma v or sigma h. Finally, instead of sigma xy xz yz representation, it is better for you to go by sigma b or sigma h. That will be more useful for our group theory considerations. This is with respect to plane of symmetry. We have chosen some simple examples such as water, ammonia, BCl3 and ethylene. Also we have tried to differentiate what is a sigma v, what is sigma h and what is sigma d. For sigma d we will take a couple of examples. Sigma d will confuse, it will definitely confuse you, but our job is to remove such a confusion. So whatever confusion that we create, we also destroy it. Let's take a tetrachloroplatinate. We identified C4 as the principal axis. To get the knowledge of a dihedral plane, we should have a reference of C2s. Only when there are C2s, then we can identify a dihedral angle. From that dihedral angle, plane will be bisecting or subtending. That plane will be bisecting that dihedral angle. So try to identify the dihedral angle by projecting C2s. C4 is not important now. With respect to C4, which is the principal axis, C2s are subsidiary axis. Now let us try to draw the planes present in PTCl4 first. For PTCl4, how many planes are present in PTCl4? First you try to identify. This is how I am showing you the PTCl4. C4 is the principal axis. Along with C4 we also have C2s, 4 C2s put in two different sets. This is one C2 passing from the two chlorines, second C2 passing from the two chlorines. In between also we have a C2. You may hold it this way, C2 and a C2. So to differentiate between them, what we said is, this you can take it as a C2 and a C2. This and this you can take it as C2 prime and C2 prime. So these two form one set, these two form a second set. C4 is the principal axis. How many planes are present? First we will identify, then we will try to label them, or we will try to give some identification to those planes. This is a planar molecule, so definitely we will have a molecular plane. With respect to the principal axis pointing towards you, this molecular plane is perpendicular. So this becomes a sigma h. There is one plane called as a sigma h. Next, I am passing this plane. This is the principal axis pointing towards you. Okay? If I am holding it this way, this is the principal axis. If I am holding it this way, you can see this is the principal axis. If I am passing this plane parallel to this, This plane is passing from 2 chlorines. It should also pass through platinum. Every time I did not repeat, it is passing through platinum because platinum is the central atom. It will definitely pass. It is passing through 2 chlorines. One plane parallel to this sigma V. Now this one is passing through these 2 chlorines parallel to the principal axis. I can also call this as a sigma V. Let me hold the molecule this way. Between these 2 chlorines, I am trying to pass another plane. Just as we passed C2, C2, C2 and C2, similarly pass a plane, parallel to the principal axis, sigma V, sigma V. Then try to pass a plane from here. This is also bisecting the molecule into symmetrical halves. This also becomes a sigma V because it is parallel to the principal axis. Then I try to pass this plane. This plane is also parallel to the principal axis, therefore I am calling this plane as a sigma V. Apart from this, do you find any other planes in this? You don't find any other plane. I am showing you the planes. This is one plane, molecular plane, but since it is perpendicular to the principal axis, this is called as a sigma H. This is a sigma V, this is a sigma V, this is a sigma V, and this is also a sigma V. 1, 2, 3, 4. All are parallel to the principal axis, therefore 4 sigma V's. One is perpendicular to the principal axis, therefore it should be a sigma H. This is with respect to a principal axis, remember. So with respect to a principal axis, whatever planes now I am drawing, this I am calling it as a sigma H, this I am calling it as a sigma V, sigma V, sigma V, sigma V. This convention is with respect to principal axis, not PLE, it is PAL. This is with respect to principal axis. You just go through the definition of dihedral plane. What is a dihedral plane? Means it is a plane that bisects the dihedral angle. Then what is the dihedral angle? It is the angle subtended between 2 similar consecutive C2s. Do we have any C2s in this? The answer is yes, we have C2s. Then again we will try to draw C2s this time. I am not numbering it because we are not doing any operations right now. We are trying to understand. Simply I am representing them. You need not operate and show the other structure. This is one C2. This is a second C2. This is a C4. I don't know whether you are able to differentiate between the colors, if it is visible to you or not. If you are looking in laptops or PCs, then it will be much more visible for you. This particular C2 that is passing from 3 atoms I have taken in orange, and that particular C2 which is passing only from platinum I have taken in yellow. To differentiate between them, I am taking this as C2, whereas this I am taking as C2 prime. Because between these two, if at all I have to assign any priority, this is passing from 3 atoms, so greater priority. This is passing only from 1 atom, lesser priority. C2, C2 prime. C2 and C2, there are 2 C2s, C2 prime and C2 prime. So there are 2 sets of C2s. This is one and this is another one. What is by definition dihedral angle? Dihedral angle is an angle subtended between two similar and consecutive C2s. Similar in the sense, now don't compare this similar to the beginning one what we have discussed, same and similar. Here what similar means, this is a C2, this is a C2 prime. Between these two there is an angle. Next, this is a C2, this is a C2. Between these two also there is an angle. Which angle should we consider means, you have to consider that angle which is between the two similar C2s, not different C2s. These two are different. One is C2, another is C2 prime. One is passing from 3 atoms, the other one is passing only from 1 atom. So these two are different. But these two are similar. You cannot call them as same, because if this is one C2, this is another C2, therefore we don't say same, they are similar. 3 atoms, 3 atoms. Okay. So it is that angle subtended between two similar consecutive C2s. Consecutive means one after the other. Since in this example we only have two such C2s, you need not say consecutive, because that will be consecutive. Now let us put that angle. Between this and between this C2 there will be some angle. That angle I am calling it as a dihedral angle. Don't take the angle between C2 and C2 prime. Don't take it. It is not a dihedral angle. It is an angle subtended between two similar C2s. Or if I take a C2 prime and a C2 prime, the angle between them is also a dihedral angle. Don't take it between prime and C2. You just take it between a C2 prime, C2 prime, or you take it between C2 and C2. It is up to you. But they must be similar. They should not be different. If you just follow that guideline, it is very easy for you to understand. Two similar C2s or two similar C2s, but not different C2s. Based on this definition, now let us try to get the planes. This is a C2, this is a C2. C2 prime, C2 prime, which one will get a priority means C2 will get a priority. So with respect to this priority, this theta I am taking it as a dihedral angle. This blue one I am not taking it as a dihedral angle. There are two possibilities. This is one possibility of a dihedral angle, second possibility of a dihedral angle. But first possibility is getting a more priority, because C2 has a greater priority. Between these two there is an angle called as a dihedral angle, and any plane that bisects this dihedral angle should be called as a dihedral plane. Then this becomes sigma d. This becomes sigma d, because again this is C2, C2. Between these two there is an angle. It is not continuous one. From here to here, stop. From here to here, you stop. You can just rewatch the video at this point. You need not get confused. Here I have shown that there are 4 sigma b's. Now here I am showing that there are 2 sigma d's. What about the other 2 planes? These 2 planes are considered to be sigma b. C2 gets priority over C2 prime. Between two consecutive C2s there is an angle theta, and whichever plane that is bisecting that theta should be called as a dihedral plane. Similar is with this case. The remaining plane is parallel to the principal axis, therefore I am calling it as a sigma b, sigma b. Which one is correct? In the first case I am saying that there is 1 sigma h plus 4 sigma b. In the next case still there is a sigma h. If you want you can represent it. In this case there is 1 sigma h, 2 sigma b, 2 sigma d. which convention should we follow? That will be a little bit confusing one. Now if you stick very strongly to the definition of a dihedral plane, even this you should call it as a dihedral plane. Why should you call this as a dihedral plane? Because this is a C2 prime, C2 prime, LO, right, C2 prime, C2 prime, that is making some angle, C2 prime, C2 prime, making some angle, and any plane that bisects it should be called as a dihedral plane. So this should be a dihedral plane, this should also be a dihedral plane, if at all we stick to the definition of a sigma d. Then that becomes a third convention. This is the first one. This is a second convention, and according to that third convention, even this will become a sigma d. I am not drawing it, space is not enough, but you can just imagine, because by definition between these two C2 primes there is an angle, plane bisecting that dihedral angle should be called as a dihedral plane. So according to the third convention, I get 1 sigma h, 4 sigma d. Which one is correct? It is up to the author. It is up to the author. Our understanding is, with respect to the principal axis, there should be 4 sigma v's. But with respect to the definition of a dihedral plane, there could be 2 dihedral planes if we give priority to the sigma v's. If you don't give any priority to the sigma v, don't give any priority to the principal axis, then there has to be 4 sigma d's. In the examination they will mention whether they are giving you 2 sigma v, 2 sigma d, or they are giving you 4 sigma v. So don't get confused with that. But for group theory considerations, generally they take 2 sigma v, 2 sigma d. But for illustration purposes, we generally take this convention, 1 sigma h, 4 sigma v. When we jump into group theory character tables, usually we find it this way, 2 sigma v, 2 sigma d, etc. This is one other convention some authors follow. So at this point you need not get confused absolutely. It depends on authors in which way they are considering. There is no hard and fast rule that you have to say only 4 sigma v, you have to say only 2 sigma d, 2 sigma v. It is up to our understanding. You need not bother about it. Even when it comes to the plane, in the examination, suppose by convention we take this as z, x and y. In the exam, while they ask the question, they may change the convention. They will put this as x, this as y and this as z. So they may put x, y, z, then they will ask you, there is some rotational axis along z. So whenever they are asking a question that a rotational axis is passing along z, then you pass it like this. Always don't put that this is z, this is x and this is y. This is for our illustration purpose, standard convention. If at all they are changing the convention, it is up to them. In the exam, the examiner may change the convention, but look it carefully. They may also say that one particular molecule has 4 sigma v, or they may give you 2 sigma v, 2 sigma d. In both ways they are right. Let it be an understanding question or an applicative question. My only motto, or our institute's only motto, is every student should be able to write any understanding or even applicative kind of a question. So for this reason we explain all these things in detail, or else simply we can give one example for sigma d, one example for sigma v, that is completed. It is not so. If you could remember in the regular classes, I always say that any question paper, any standard national level examination question paper is set on 3 different bases. One is knowledge, one is understanding, and the third one is applicative basis. CSIR GATE exams will mostly have understanding and applicative kind of questions. You will also find knowledge kind of questions. Knowledge kind of questions means you don't need to put, or don't need to understand and apply the question. Simply if I ask what is the atomic number of neon, that is simply knowledge. If it is there in your knowledge, you will directly put it as 10. But you don't try to understand, okay, how many protons are there, how many neutrons are there. No need of any understanding and application. It is direct knowledge question. But if at all they ask about its isotope, neon, or say they have taken some other chlorine, they are asking you the isotope, and they are asking the mass spectra, etc., then you need to have some understanding. That understanding with the knowledge that you have to apply. So if you have to understand and apply, you definitely need some stronger subject. Okay, always don't go for shortcuts at this higher level. But once we complete the units and as we take up some question papers, at that time we will give you some logics, how to identify it easily. If you are not able to understand those logics, then go by the standard subject that we are teaching. We have seen different planes for PTCL4. Now let's take a benzene example and let's differentiate what kind of planes are present in this. First let's identify the principal axis, it is C6. After this C6, now we have a C2 passing from the opposite corners. We are just calling these as corners. Then from the opposite edges, we have another set of C2s. To differentiate them, let's put a prime for it. Benzene has a C6 and 6 C2s perpendicular to the principal axis. With respect to this principal axis, whatever plane that is present, that plane, whether it is parallel to it or perpendicular to it, has to be checked first. Now let us try to pass this plane. When I am passing this plane is parallel to the principal axis. So from here I will show. Suppose if I am passing a plane from the opposite pair of a corner, that particular plane will bisect the molecule into symmetrical half, which are mirror images to each other, and it is parallel or along the principal axis, therefore I can call this plane as a vertical plane. Likewise, I can also call this plane, which is from this pair of corners, that is also parallel to the principal axis. Principal axis is pointing towards you and this plane is parallel to it. Principal axis parallel to it, sigma v. Principal axis parallel to it, sigma v. And this particular plane, if I pass here, that is also parallel to the principal axis, therefore I can also call this as a sigma b, right. So a plane that is passing through the through the principal axis or which is parallel to the principal axis can be called as a sigma b. We have 3 pairs of corners, therefore there are 3 sigma b. Also come to the pair of edges. From this pair of edge, if I pass a plane, one half is a reflection of the other half, but even this plane is parallel to the principal axis. Come to the second set of edges, this plane is also parallel. Come to the third set of edges, this plane is also parallel. By convention, I'll draw it here. By convention, let's call all these planes as sigma b because they are parallel to the principal axis. Apart from that, we also have a sigma h, a plane which is parallel, a plane which is perpendicular to the principal axis. So in this case, let me represent, this is a C6 and we have C2s here I have represented. I am not putting the same here because in this case I am trying to represent the planes. This is one plane, second plane, Every time I need not put the full plane. And a third one. One, 2 and 3. Since they are parallel to the principal axis, let us call them as sigma v. Now this plane is also parallel to the principal axis. This is also parallel to the principal axis. Sigma v, sigma v. Finally, this plane we are also calling it as a sigma v because all these planes are parallel to the principal axis. We have a molecular plane which is a sigma h. There is a sigma h, along with that we also have 6 sigma v. Now look at this rotational axis again. Here this is a C2. I am just putting a full C2. This is one C2, this is a second C2, and this one is a third C2. C2, C2 and C2. Whatever angle that is present between two similar, C2, C2 are similar, C2, C2 are similar. So an angle present between two similar, this and this are also similar, and consecutive C2s. Consecutive means one after the other. In this case, I may take from here to here, C2 and C2 are similar, or I may choose an angle from here to here. Which one is correct dihedral angle means, in the definition what we have seen is, dihedral angle is an angle subtended between two similar, this and this are similar, this and this are also similar, two similar consecutive C2s. Consecutive means one after the other. So after this C2, immediate C2 is this. Hence you have to consider this particular angle as dihedral angle, but not this one. You may also take between these two. This will also become a dihedral angle. This will also become a dihedral angle. But from here to here is not a dihedral angle. Therefore, the definition is very important. It is an angle between two similar but consecutive C2s. Not a not a alternate one. It is a consecutive C2s. Okay. So with respect to that definition, now this is becoming a dihedral angle. Any plane that bisects this dihedral angle, this is a dihedral plane. This should be a dihedral plane. So any plane that bisects this dihedral angle should be a dihedral plane. Therefore, a plane that is passing from the opposite pair of edges should be called as a dihedral plane. Not this one, from the opposite pair. Let me put it here. Just as in the previous convention for PTCl4, what we have done is, we can have 1 sigma h 4 sigma v convention, 1 sigma h 4 sigma d convention, 1 sigma h 2 sigma v 2 sigma d convention. In a similar manner, even for benzene we can have 1 sigma h. Every time I will not repeat sigma h. There could be 6 sigma v convention, there could be 3 sigma v 3 sigma d convention, or there could be 6 sigma d convention, because if at all I consider C2 prime and C2 prime, there are 3 C2 primes. They are similar. Consecutive is these two, or consecutive is these two. Consecutive, consecutive, consecutive. So between them there will be a dihedral angle, and a plane bisecting them will be a dihedral plane. Based on that, suppose if I choose a C2 prime, C2 prime, you can just watch. if I just extend this C2 prime, C2 prime, this particular angle is called as a dihedral angle, and this plane should be called as a dihedral plane. Then even this will become a dihedral plane according to a second convention. If there is no dihedral plane explanation, simply every plane that is parallel to the principal axis will become sigma v. If at all C2 definition is also considered, then there should be 3 sigma v, 3 sigma d, or all 6 sigma d along with a sigma h present in it. Which convention will you follow? It is up to you. That depends on the examination and the type of book that you choose. In some books it has been given as 6 sigma v for benzene. In some books you find it as 6 sigma d. And for group theory considerations, you will find 3 sigma v, 3 sigma h also. 3 sigma v and 3 sigma d. 1 sigma h is anyway present. This is for benzene, previous one was PTCl4. Whether it is PTCl4 or benzene, the principal axis is odd even number. That in that case it was C4, in this case it is C6. Suppose if I choose a odd number means, suppose if I am choosing CP anion, cyclopentadienyl anion. If I am choosing a cyclopentadienyl anion, in cyclopentadienyl anion there is a C5. So with respect to this C5, whichever plane that is present should be called as a sigma v. This is one plane, each plane is passing from a corner and the opposite edge. Just similar to C2. C2 was also passing in a similar way. It is taking up one corner and a opposite edge. Similarly, each plane is also taking a corner and the opposite edge. Sigma h is anyway present. Now with respect to the principal axis, all these I am calling it as a sigma v. Five. 1, 2, 3, 4, 5. If you want, you can just extrapolate the lines to just identify these planes. These are the 5 planes, and sigma v is according to the definition as they are parallel to the principal axis. Where are the C2s? This is one C2, each C2 is passing from a corner and the opposite edge. If this is one C2, second C2 is coming here, third C2, fourth C2 and fifth C2. Between these two C2s, if at all, I will try to draw two C2s in yellow. Suppose if this is one C2, here we have a second C2. I am just extending them. So between this C2 and this C2, and also let me put a third one. Here is another C2. Fourth C2. Okay, I have put all the C2s. All the C2s are here now. How many different types of C2s are present here? In the case of benzene, in the case of PTCl4, or wherever the principal axis is even numbered, we have seen two different types of C2s. One C2 was passing from the opposite corners whereas the other C2 was passing from the opposite edges. Whereas when the principal axis is odd numbered, there is only one type of C2, and that one type of C2 will pass from a pair of corner and an edge. So whichever C2 that you choose, suppose if this is the C2, it is a edge and a corner and a edge. So there is only one type of C2. Since there is only one type of C2, the convention goes this way. Either all these I can call it as sigma V, or all of these I can call it as a sigma D. Because if this is one C2, second C2, third C2, fourth and fifth, right? Out of these 5 C2s, 2 similar, all are similar, consecutive. Consecutive means these two is a theta. Between these two is a theta. So you may choose any 2 similar consecutive ones that become a theta. And any plane that bisects this dihedral angle should be called as a dihedral plane. So according to that definition, every plane will become sigma D, or according to the principal axis convention, every plane will become sigma V, right? So for the odd numbered molecules, for the molecules where the principal axis is odd numbered, we have only 2 conventions. First convention is one will be a sigma H plus all are sigma V's with respect to the principal axis. Second convention is one is sigma H, all the others will be sigma D. It is not that half of them are sigma V, half of them are sigma D. Half is not possible because these are odd numbered. You have 5 planes altogether which are parallel to the principal axis. 3 sigma V, 2 sigma D you cannot call, that is not possible. So only 2 conventions appear for odd numbered principal axis molecules. One is sigma H 5 sigma V, or sigma H and 5 sigma D. Whereas for even numbered, you can have 1 sigma H 6 sigma V, 1 sigma H 6 sigma D, or 1 sigma H 3 sigma V 3 sigma D. This is how it goes when it comes to the dihedral plane. So when it comes to the character table, half of the, suppose if I choose benzene, half of the planes can be represented as sigma V, half of the planes can be represented as sigma D for even numbered one. For odd numbered one, either they have to represent as V or they have to represent as D. Half of the representation is not at all possible for odd number. Where to use this sigma D and where not to use it, we will discuss with the help of some logics. Because whichever molecule that we choose, whichever is planar, then we will have a doubt with respect to principal axis should I go, or with respect to C2 should I go. We will just clear off that doubt. Remember this most important logic, or just I am giving it as a guideline. To identify sigma D. In which kind of molecules we have to invoke the concept of sigma D. Only that guideline I am giving you. Whatever molecule that has been given to you, either you follow sigma V or a sigma H convention, but try to invoke the concept of sigma D only for these particular kind of molecules until and unless they ask in particular. Okay. Particularly if at all they ask, only then you go for it. Otherwise you can just follow this guideline. There are some molecules where there are identical units. There are some molecules where there are identical units within the molecule. Let me give an example. Suppose if I am taking an example, I am taking an example of ethylene and allene. 2 examples I am taking, one is ethylene, one is allene. In case of ethylene, there is one CH2 unit, which is identical to the another CH2 unit. So we say that there are two identical units, minimum of two identical units. When it comes to the allene, there are two identical units, CH2, CH2. But how are they oriented, you check. In case of ethylene, if at all you are looking from this direction, this CH2 is exactly eclipsed over it. Whereas in the case of allene, it is like they are staggered to one another. One CH2 unit is staggered to another CH2 unit. Right? Now, way to bring out the sigma d concept means, in whichever molecule, when you have two identical units, CH2, CH2, it should not be like CH2 and CF2, etc. CH2, CH2 are identical units. In such molecules where you have two identical units that are staggered to one another, in such a case, if a plane is present, put that plane as a sigma d. One easy way to remember. Identical units staggered, then you will have sigma d. If the identical units are eclipsed, then in such a case you will have sigma v, sigma h kind, but not sigma d. If they are eclipsed, sigma v, sigma h concept. If the identical units are staggered, bring out sigma d. There will not be any sigma h in this case. Let us take an example which is a most popular and most important example. Let us take the example of allene, and for our illustration purpose, this is how I am taking the allene hydrogens. For convenience, I am just writing them in a clockwise manner. 1 and 3 are on the carbon which is towards you, 2 and 4 are on the carbon which is away from you. So I did not extend this line. In this case, first of all, we have to identify where the principal axis is present. So that principal axis is pointing towards you. This is the principal axis which is pointing towards you. This is a C2. And whenever you get molecules where two identical units are staggered to one another, when you put in such a kind of a projection, which is much convenient for us, I said some grooves will be forming, some spaces, and from these opposite grooves, C2s will pass. So this I am calling it as a C2, this is also a C2. Since these two C2s are passing only from the central carbon, whereas this C2 is passing from 3 carbons. So this will become the principal axis and these two will become the subsidiary. For convenience, I am extending them. As I extend them, you can watch, this is a C2 prime, this is also a C2 prime. Or you may take these two, C2 prime, C2 prime, C2 prime, C2 prime, C2 prime, C2 prime. Two similar C2s, there are only two C2s, therefore they are consecutive only. They make an angle, and that particular angle we are calling it as a dihedral angle. Or in a similar way, here we take these two C2s, they are making some angle, dihedral angle. Any plane that bisects this dihedral angle should be called as a dihedral plane. So if this is the theta, the plane that is bisecting it should be called as a sigma d. And if this is the theta, plane that is bisecting it should be called as a sigma d. You just don't call it as a sigma v, you simply call it as a sigma d. You can also call it as a sigma v because this is the principal axis, but our guideline says whenever you have two identical units that are staggered to one another in such a concept, you try to invoke sigma d only. Don't try to bring the concept of sigma v here. If they are eclipsed, then you can bring the concept of sigma v as well as sigma h. Since this is at competitive level, you should be knowing the logics and the easiest way to remember. One easy way to remember is whenever you draw all such molecules where two identical units are staggered to one another, some spaces are formed, we are calling it as groups. From the opposite groups, C2s will pass. Whereas from the opposite corners, this I am calling them as corners. In this case they are atoms, but according to their position I am calling these as corners, these as corners. From the opposite corners, sigma d will pass. From the opposite corners, sigma d will pass. From the opposite groups, C2s will pass. Remember this thumb rule, just remember it, it will be very, very easy for you. I will also show you one more example, that is for allene. Now let me take ethane. Whether our guideline is being applied to some other molecules where there are two identical units, let's check. This is an ethane, one CH3 unit, other CH3 unit. Both units are identical, but this is an eclipsed conformation. So from eclipsed, I am just getting it into skew or gauche, then slowly I am converting it into a staggered form. Okay. This staggered conformation I am drawing it. Now these three hydrogens are away, that I am representing with yellow. We have two identical units, hydrogen on the front carbon is above and this particular hydrogen below is this one on the rear carbon or the back carbon. For all such molecules, there will be some groove, and from that groove, as I said, C2s will pass, and from the opposite corners sigma d will pass. So just by looking at the molecule, whatever logic that I have told you, you can immediately identify where the C2 is present and where sigma d is present. This is the molecule. From here we can identify there is a triangular relation. So we can have a C3. C3 is possible, that is passing from the two carbons. From sideways also I am showing you. There is a C3 that is present. I have to rotate 3 times. Once, twice and thrice. So while I rotate, you just keep your eye on one of the atoms, that take it as a reference, and then as I rotate, if this is the reference, 1 that is going towards the left hand side, 2 that is coming towards the right hand side, and third time on top. In such a representation, as I told you, now here some spaces are being formed. So from these opposite grooves, C2 will pass. Here is a C3 principal axis. From the opposite grooves, C2 will pass. From the opposite groove, C2 will pass. From the opposite groove, groove means a space. From the opposite groove, C2 will pass. This is an atom, this is an atom. If I don't put that atom, this will be just like a corner. From the opposite corners, sigma d will pass. If this is a corner, opposite is this. So from here, sigma d will pass. From the opposite corners, sigma d will pass. From the opposite corners, sigma d will pass. Whatever may be the molecule, when you have two identical units staggered, you just put C2s from the opposite groups and pass sigma d's from the opposite corners. This is one way to represent such molecules. Also, let me show you another way to represent them. If you can look at this molecule carefully, I am connecting H1, H2 and H3. It is forming a triangle. Also, I connect H4, H5, H6. That is forming another triangle. There are two triangles that are staggered to one another. I am drawing these triangles here. This is one triangle. Now there is a second triangle which is away from you. And that triangle towards you is fully solid, whereas this one I have represented by dotted lines. 1, 2, 3, I am simply numbering it as 1, 2, 3. They are hydrogens. And this was 4, 5, 6. Now when I represent it as a triangle, you can see the spaces. It is forming a notch. It is forming a notch. There is a notch. So from such opposite grooves, C2 has to pass. From here and from here, C2. And from here and here, C2. This is a corner, opposite is another corner. So from the opposite corners, sigma d. From the opposite corners, sigma d. And from the opposite corners, sigma d. This is the principal axis C3. So C3 is anyway present. Along with that C3, we have 3 C2s that are perpendicular to C3, and we also have 3 sigma Ds. This is in the case of a staggered ethane. If at all I choose any such molecules where there are two identical units, put them in these kinds of projections, and then search for the opposite groups. In the opposite groups, you will get C2, and from the opposite corners, you will get sigma D. This is how you can represent dihedral planes. If it is a single unit in the sense, suppose it could be a PTCl4 or BCl3 or cyclopentadienyl anion or benzene. For all such units, tropylium cation, cyclooctatetraenyl dianion, for all such single units, put the concept of sigma H as well as sigma V. In this case, only sigma D's will be present. You don't find any sigma H. Either I hold a lin, this is the principal axis pointing towards you. If I hold it this way, this is the principal axis passing from the 3 carbons. There is no sigma H. Why there is no sigma h? Suppose if I am holding it this way, imagine that this is a sigma h. This half which is towards your right hand side is in the vertical plane. With respect to you, this is a vertical plane, not with respect to the molecule. Or I am just saying, if vertical plane, horizontal plane you may confuse, it is in this plane. When I pass a horizontal plane, now this will reflect this way, but it will not reflect this way. So after passing this plane, this is how it will reflect. These two are not similar, they are not equivalent, they are not identical, therefore I cannot pass a sigma h. But I can pass a sigma d. Where is that sigma d? You can check. That sigma d is this. The second one is this. One sigma d, second sigma d. If I am holding the molecule in this manner, this is one sigma d, second sigma d. Each sigma d or a dihedral plane is taking up 3 carbons. Along with that, it is taking 2 hydrogens at a time. If this is this plane, taking these 2 hydrogens, coming out between these 2 hydrogens. If it is this plane, it is between these 2 hydrogens, and as it come out, it is taking up these 2 hydrogens. So sigma d is taking 2 hydrogens at a time, 2 hydrogens at a time, right? C2s I have shown in the last class. Suppose if this is how I hold the allene, here is one C2, here is a second C2. When it comes to the staggered ethane, principal axis is present here, and for C2s this is how we can watch. You have to just see this like a X. In that X, 1, 2, 3 and 4 arms. So from here is one C2. Okay. When we discuss the point groups, there whatever example that we take, how the rotational axes are present, how the planes are present, I will show separately. Here we are checking for a dihedral plane. Where is a dihedral plane means, imagine that I am holding the molecule this way. This is the principal axis. Principal axis. Okay. Different orientations I am showing you. I cannot pass a sigma h because one hydrogen on top cannot reflect with 2 hydrogens on top. Sigma h is absent, but here is a sigma d. With respect to principal axis, you may consider it as a sigma v, but our consideration is 2 identical units staggered to one another. Don't call it as a sigma v, call it as a sigma d. Each sigma d, as it passes, it is taking one hydrogen, carbon, carbon and a hydrogen. So this is one sigma d. Second sigma d will take up these 2 hydrogens, and third sigma d will take up these 2 hydrogens. Okay. So here it is this 1 and 5, 1 towards you, 1 away from you, then these 2, then these 2, 1 towards you, 1 away from you. This is the case of staggered ethane. You can also work out with ferrocene, you can also work out with chromocene or bisbenzene chromium or dibenzene chromium. When the 2 units where the metal is sandwiched between the 2, when the 2 units are eclipsed to one another, we can have a sigma v and a sigma h, but when the 2 units are staggered to one another, sigma h will be absent, whereas sigma d's will be present. Don't consider them as sigma v's, consider them as sigma d's. That is your assignment. You just try to draw the structures of ferrocene as well as chromocene. And how do you represent that ferrocene, chromocene? Because the metal is sandwiched between them, you have to go in this kind of a representation. You just cannot go in the other way. Okay. Suppose if I say ferrocene This is how we represent a staggered one. Edge is towards you. In the above cyclopentadienal ring, edge is towards you. Whereas in the below ring, corner is towards you. So this is a staggered ferrocene. But if the two rings are eclipsed, then both edge will be towards you or both corners will be towards you, that is a eclipsed. In this case I am taking a staggered one. By taking this, showing the dihedral planes or showing C2s will become difficult. What my suggestion is, it is a straight view of a ferrocene. Suppose if I am holding ferrocene this way, we cannot show with these models. Suppose if this is the ferrocene you are looking from here. Don't look it from here, just look it from the top or bottom. When you look it from top or the bottom, it will be like both rings that are staggered. If this is the case, now draw the molecule in such a way that you are looking them this way, just as you have done it for staggered ethane, where the two units were two triangles that were staggered. Now the two units are not triangles, they are just like pentagons. Put two pentagons staggered over one another. Then you will get some spaces. Through that spaces, try to draw C2s, and through the corners, opposite corners, you just try to put sigma d. Likewise, you also take chromosine. I am putting it here. This is a staggered chromosine. And this is a ferrocene, staggered. You should have a top or a bottom view. Top or a bottom view. Put the two pentagons just as two triangles that you have put staggered. Put two pentagons as staggered from the top view. Here also put two benzene rings staggered to one another. Not this view. Now from the top view you have to draw it this way. Then try to show the C2s and sigma Ds. That is for your assignment. In our next class I will try to show some more examples. And once we complete this plane, we have to enter into another symmetry element, which is a combination of a rotational axis as well as a plane, that is SN. Once we complete SN, inversion element is a very shorter element, just a couple of examples that will be fine and very easy to understand also. Identity, it is a doing nothing operation or a doing complete operation, so we need not bother about the identity element also. Only concern is with the rotational axis, plane, SN and inversion. So based on this, you must be able to identify the point group of a given molecule, then we will slowly enter into the group theory, we will study the character tables and the spectroscopic properties. With this I will complete this class.